Hello, am I audible? Uh, Hello, everyone. Am I audible? Like, we just, yes.
Hello.
Yeah. So, am I audible? Fine. We'll wait for some few more minutes. So that some few more students can join, and then we can start. So, and I kindly request, like, if you are just don't want to speak anything, like, if you don't have any queries, just please mute your mic so that there's no any disturbance. Thank you. Okay. I think students will eventually join. So let me introduce myself. I am Abhishek Sarkar, and I am one of the TAs for the course Introduction to Fluid Mechanics, conducted by Professor Suman Chakraborty, and we are here to discuss about some of the concepts for week 2 of the NPTEL course, and discuss some of the simple problems so that you can grasp the concepts that have been taught in the class. So, based on the content of the course that I have seen, I guess these are the topics that have been taught: density, bulk modulus, viscosity, then Newtonian fluid, kinematic viscosity, and also non-Newtonian fluids. So, do you, among all of you, do you have any doubts regarding these concepts? Like, you can ask if you have any doubt. So you're free to ask. Okay. So I think it's fine, but I like to keep the session a bit more interactive. So I will ask some questions. You may either unmute yourself and tell the answer, or just write it on a chat. So that's completely fine. And I see there are many. Tarun, if you have any question, you can ask, or else please mute your mic. So it's, I'm getting unmute. Yes, thank you. So I guess I see there are lots of new students in this session compared to the previous session. So uh, if you have any queries regarding this week two's topics, you can please ask, or else I will ask questions and you will just have to answer so that I can see how clear you are regarding the concepts. So please, for a few minutes I will wait if you have any queries. Okay, then I guess there's no queries. So now I will ask questions. So you kindly answer. It will be very good if you all of you cooperate with me, so that I can make this session as interactive and as enjoyable as possible. So yeah, first of all, I'll just ask about very simple concept of viscosity. So what do you mean by viscosity? Like, what significance does it play in a fluid flow? So any one of you, please unmute yourself or just write in the chat. That's completely fine. Please feel free to interact, or else there is no point of having these sessions. Okay, then, no problem. Um, so let me ask: have you attended the week 2 lectures in the SWAYAM portal for this course? Yes, no will be fine. Then accordingly, I can just modify the content that I speak today. Otherwise, it will be very difficult if you have not attended the sessions, lectures, and just have came to the session. So it will be very challenging for me. So please say yes or no. Have you attended this week 2 lectures for the Introduction to Fluid Mechanics course in the SWAYAM portal? Dhanlakshmi, Nikhil, Rameshwaran, Ranjan, Rishi, Tarun, any one of you? Have you attended the lectures in the SWAYAM portal? Kindly respond. No, if no, that's also fine. Yes, it's also fine. Like there's no hard and fast rule that if you don't attend, you cannot attend the session. Because if you don't speak, then I will assume that you have attended the session, and then I'll teach. I will take the session accordingly, and don't go deep in the concepts. If you don't say anything, I will assume that you have attended the sessions. I'll wait for a few minutes. If no, then I'll just continue with the session, and I guess that will be it for today, I guess, from my side. I'll point out then. Dhanlakshmi, can you hear me? Hello, Dhanlakshmi? Okay, it's fine. Have you attended the week 2 lectures for this course? That's fine. Nikhil?
Sir, am I audible?
Yeah, you're audible. Yes. Have you attended the lectures, the week 2 lectures for this course?
Sir, I attended the week 2.
You have attended, right?
Yes, sir.
Oh, that's very good. So I have asked a question regarding viscosity. Could you please explain like what viscosity is or what's its importance?
So viscosity is the measure of fluid resistance over one plate to another.
Okay. Yeah. That's right. That's absolutely right. In that, I think like you need not need to mention any plates. You mentioned plate, right?
Yes, sir.
Yeah. Plate is fine. There's no reason of it's fine. Like, but it's not necessity that only for motion between two plates only viscosity plays a role. See in this diagram that I've given in the screen, it does not have any plate, other plate. There's no plate above it. So there is only one plate, and there is a fluid flow which generates a boundary layer, but still the viscosity exists. Actually, viscosity is a fluid property which resists the motion of the fluid against any solid surface. You can keep it that way, and what you said is absolutely correct. So there is no hard and fast rule of the existence of two plates to define viscosity. Is that clear? It's clear, I guess. It's fine. Thank you, Dhanlakshmi. It's very good that you have at least spoken up. So yeah. So just as Dhanlakshmi has explained very beautifully. So you can see in this diagram, I'll just point out here now. Yeah. So in this diagram, you can clearly see there is a flat plate given by this black colored trapezium. That's fine. This is a flat plate. Say there is a flat plate, and there is a fluid flow moving with a velocity u infinity. So if you have attended lectures, you will clearly know what u infinity basically means. So u infinity basically implies the free stream velocity or the undisturbed fluid velocity that approaches this plate. So once this fluid layer, this undisturbed fluid layer strikes the plate, what happens is the fluid layer at the bottom layer, the fluid that is in contact with the upper surface of this plate sticks with the surface of the plate. The fluid molecules try to stick with the surface of the plate, and what it does is, I will just zoom out a bit.
Sir, there is a problem in assignment 3.
I'm sorry, who is speaking? I have to see who is speaking. Ranjan, yeah.
Sir, there is a assignment is problem 3. Assignment 3.
Yeah. See, Ranjan, thank you for asking. But the thing is, these sessions are not meant for giving solution to the assignment problems, rather to clarify the concept that you are reading in the class. And these sessions will be just a week before the assignment, the assignment number that you have to submit. So you understand, right? So, but I will still encourage you to ask the doubt.
Okay.
Like, if you have any doubt, just give it in the chat box. That would be fine, so that I can just contact you personally and help you out. Okay? Is that fine, Ranjan?
Okay, sir.
Okay. I hope you understand. Yeah, no problem. Thank you. Okay. So, what happens is the fluid molecules that are in contact with the plate become stationary and have zero velocity. So what these fluid molecules try to do is they try to slow down the fluid molecules in the layer above it. But simultaneously, the fluid layer above these molecules tend to increase the velocity of this. I will just number it, point it out here. The fluid molecules in the layer 3 tend to speed up the velocity of fluid layers at layer 2, but the fluid layer at 1 tends to slow down the velocity of the fluid molecules at layer 2. So this simultaneous effect of slowing down and speeding up generates this kind of velocity profile, this well-known velocity profile. And this slowing down effect, or the phenomena by which the fluid molecules sense the presence of this plate, is known as viscosity. It's because of viscosity only, that these molecules sense the presence of the plate and try to slow down, and forming this parabolic, I would not say parabolic, this shape, the velocity profile of this shape. I guess that would be a clearer explanation. So I guess this is fine. So now let's come to some questions. Like, say there are two fluids flowing on. There are two types of fluid flowing in above this flat plate. Okay, say there is fluid 1 and fluid 2. Say fluid 1 has higher viscosity, and fluid 2 has lower viscosity. So given these conditions, where do you expect the boundary layer to be thicker? You understand boundary layer, I guess, like just the vague concept of boundary layer itself. Like this diagram shows what a boundary layer, but I guess you have, from the week 2 lectures, you have a vague or like slight understanding of what boundary layer actually is. It's basically the point up to which the velocity is the 0.99% of the u infinity. So this layer at which the velocity is 0.99 of u infinity is known as a boundary layer. So given this, where do you expect the boundary layer to be thicker? For the higher viscosity fluid or a lower viscosity fluid? You can write on the chat, or 1, 2, like anything. That will be fine.
Higher viscosity.
Higher viscosity. For thicker boundary layer, right?
Yes.
Yeah, you're absolutely correct. So I guess I have written the explanation also. It happens because the disturbance of the momentum imposed by the plate is propagated to a greater distance. See, higher the viscosity, higher the fluid will feel the presence of the plate, like at a higher, what to say, it will have a higher tendency to feel the presence of the plate. So to so to so in a natural sense, what happens is the boundary layer becomes thicker as the viscosity increases. So if I draw another boundary layer, say this one.
Sir, I want solution of assignment 3. Problem is happening.
Which problem?
I want solution of assignment 3. Problem is happening.
Yeah, I guess it's Ranjan. Yeah, Ranjan, I told you, right? I cannot give the solution to your assignment 3. If there's any problem, please write the question on the chat or just write my mail ID. Just give me the question, because I also don't know what's the question. So please write the question so that I could review it and contact you personally, or after the session is over. Is that fine?
Okay, sir. Contact number, sir.
I will not give contact. I will give my email ID, so you can just give me the question, the screenshot, or everything is fine. So
Okay, sir. Okay.
okay. Yeah, I guess you got the email, so you can just mail me there. Okay, I'll contact you personally through your mail. I'll just reply you in the mail. Is that fine, Ranjan? Okay. Yeah. So whoever told that thicker boundary layer for high viscosity is correct. So thank you for that. Yeah, and let's continue further. So yeah. So the next concept I want to just ask you is a very vague concept again, but important one, about density. So could you please give me an idea of like what density basically means in a fluid mechanics point of view? It's a general explanation, but in a fluid mechanics point of view, what density basically means? Like, I guess Professor Chakraborty took a long time to just teach you the concept of how to choose the elemental volume. What are the conditions to choose the elemental volume to find out density? So could you please elaborate, any one of you, what density means and how to choose the elemental volume? What is the concept behind choosing the elemental volume?
The volume shouldn't be too small or too big.
Yeah, absolutely right. Who is it again? I'm sorry. Who is it?
Hello?
Prasam. Oh yeah, Prasam. Welcome back again. Yes, you're absolutely right. Why you say so that it shouldn't be too small? Because like I'm saying, because it may seem like that in mathematical point of view, like as the limit approaches 0, we get more accurate or fine solutions. But as you have pointed out correctly, that we cannot choose it to be too small. Why do you say so? Could you please explain to the class? Why do you say so? It cannot be too small.
Because the error will be more, sir. If we apply like the theory law of continuum mechanics.
Yes, you're absolutely right. Thank you, Prasam. It's actually continuum hypothesis, but yeah, you're absolutely correct. If we go to much lower, if the elemental volume is much lower than when compared to the mean free part of the fluid flow of the fluid, what will happen is there will be much more errors. Yes, much more oscillation, because there will be very few number of particles within the chosen volume, and that would give rise to errors, and that will not give a correct value of the density. Thank you, Prasam. You're absolutely correct. So I guess density is clear. So I'll just point it out again. So density can be given by delta V tells to delta V star mass per unit volume. Yeah, I guess that's fine. Oh, sorry. Where delta V star represents the volume which represents the smallest elemental volume over which the continuum hypothesis is valid. Okay, continuum hypothesis is valid. If we go below that, the continuum hypothesis does not work, and that's why we get large number of errors while measuring the density. So thank you. So could any one of you just tell me about the bulk modulus? What bulk modulus actually means, or what its significance? Please. A basic mathematical definition is also fine. We'll just then try to understand the definition. So what's bulk modulus?
Hello.
Yes, Prasam. Yes.
Sir, it is significant regarding whether the flow is compressible or incompressible.
Yeah, thank you.
With respect to change in pressure, relation between change in pressure to change in the volume or density.
Yeah, thank you, Prasam. It's absolutely correct. So, as he has rightly pointed out, it helps us to know whether the fluid is compressible or not. So, basic definition can be, mathematical definition will be given by the change in pressure, applied pressure, by the change in volume divided by its original volume, or in other way, the change in pressure and divided by the ratio of the change in density by its original density. So given this definition, what do you feel about, as you pointed out that it helps us to know whether fluid is compressible or not. So what would be the bulk modulus for a highly compressible fluid? Would it be low or high?
Sir, low?
Yes, it's correct, because see, for a given applied pressure and a given density, if the change in density is higher, then automatically, since the value of the numerator is larger, the value of K will go down. So yeah, this is a very subtle concept, but yeah, thank you to point it out correctly. Yes, that's correct. Okay. So that's fine. So given you have pointed out about compressible or incompressible fluids, can anyone please tell me about the parameter? Not bulk modulus. Bulk modulus is also one of the parameters, but the actual parameter, or the more famous parameter that we usually choose to differentiate between a compressible and incompressible flow. I guess it's a well-known non-dimensional number. So what is it? Could anyone please point out?
Mach number.
Yeah, so thank you, Prasam. It's again correct. So Mach number is actually the well-known or standard measurement of telling whether a flow is compressible or not, and it's given by the ratio of the fluid velocity to its sonic speed. Or sonic is basically the speed of sound in that medium, or in a simpler sense, the speed by which the disturbance propagate in that medium. Okay, so I guess it's clear. Sonic speed, or speed of sound in the medium, speed of sound in that medium. Okay, that's also necessary. It's not, speed of sound varies from medium to medium, so in that medium, whether it's air, water, so it varies. Okay, it's not a constant value. Okay, so that's again correct. Okay, yeah, so now we can, I guess, talk about Newtonian and and non-Newtonian fluids. Yeah. So I guess everyone knows Sir Isaac Newton. So he was a very famous scientist, and like most of the thing that we learn especially in mechanical engineering, is based on, and mathematics also, is based on the works done by Sir Isaac Newton. So I guess he is a father of all of the concepts that we learn here, and like it's very important to appreciate his works. But so I'm just mentioning because his name came out in this types of fluids, different types of fluids. So there is Newtonian and non-Newtonian fluids. So could anyone please tell me what Newtonian fluid basically means? What's a Newtonian fluid? What makes it so special that we have named a fluid to be Newtonian? Like, why is it called a Newtonian fluid?
So based on the relationship between the shear stress and the strain rate,
Yeah.
it is related for Newtonian fluid.
Yeah. Thank you. That's absolutely correct. So as Prasham pointed out correctly, for Newtonian fluid, the shear stress generated in the fluid is directly proportional to its strain rate. Okay. Shear stress is directly proportional to the strain rate. And this could actually be told as the Newton's law of viscosity. What Prasam pointed out is very accurate and like to the point, but in a vague way we can just say that any fluid that follows Newton's law of viscosity can be termed as a Newtonian fluid. That's also correct. And since you can see this equation is it's not actually the equation, it just shows how the shear strain varies with shear stress varies with the shear strain rate, and this can be converted in a equation by using a constant of proportionality, which in turn turns out to be the viscosity of the fluid, where mu is the viscosity of the fluid that we are discussing initially. So this equation is the Newton's law of viscosity. So the constant of proportionality in this is the viscosity of the fluid. So any example for Newtonian fluid, I guess, is very popular. It's fine. I guess it's very simple and most well known. It's water. It's the most commonly found liquid, I guess, in our surroundings, and that turns out to Newtonian. That's why, because of its vast applications in our day-to-day life, these Newtonian fluids play a vital role, and this relation helps us to know how the fluid may behave. Since this is the type of fluid that is found most commonly around us, and this is the relation that relates the shear stress and a shear strain rate. That's why this relation is very important or like very useful. But again, since there's a Newtonian fluid, then obviously there would be a non-Newtonian fluid, and as you can easily understand, just the inverse of what we have defined for Newtonian fluid, any fluid that does not obey the Newton's law of viscosity could be can be called as non-Newtonian fluid. But again, you may ask that, like I have now mentioned that Newtonian fluid are like the fluid that are found that are most commonly found in our surroundings. But if it is the case, then why to care about non-Newtonian fluids? See, there are some applications where we have to deal with non-Newtonian fluids, and one of the most important application where we deal with non-Newtonian fluids is in microfluidics, or otherwise in life, or what to say, in life, in biology. In biology, in this field we deal with non-Newtonian fluids, and the most popular fluid is non-Newtonian fluid is blood. So that's why we need to understand or know how to like how to say if you want to model the the flow of blood in a flow of blood in a pipe, and not pipe, flow of blood in veins and our arteries and capillaries, and we assume that our arteries are shaped as a cylinder and the blood is the fluid within it. So if you want to model it, the crucial thing to know is that now we cannot model it using our Newton's this Newton's law of viscosity. We cannot say that the shear stress in the blood, shear stress generated in the walls of the our veins could be given by this relationship, this linear relationship. No, now the relation becomes maybe we can point out like say mu theta to the power n, say like this. So in this case, this is not a linear relationship, and this also is not actually correct. I am just trying to point out a difference between these two relationships. There can be a different relationships for different types of fluids, and this relationship actually has a name. The relationship between stress and strain, it has a particular name. So can anyone please tell me like what this relationship actually called? The relationship between stress and strain. I guess it's fine.
It's called law of viscosity, no sir?
No. Law of viscosity, it is Newton's law of viscosity. Yeah, it is called it. But this relation, the relation between stress and strain, this has a particular name, a well-known name that you will encounter when you do higher studies. So actually, it's fine not to know now. Actually, it's known as
Yes, sir.
yeah. Yeah, please tell us.
Yes, sir. Just tell.
I'm very sorry, Ranjan. I couldn't hear you. Could you please write it down instead in the chat? I will wait. No problem. Please write in the chat. That would be very good. I guess it's fine, Ranjan. I hope what you are speaking was right, but I'm sorry I couldn't hear it. I'm really sorry for that. So this relationship between stress and strain is actually called the constitutive relationship. Okay. It is the standard term or standard notation that is being used to explain the relationship between stress and strains in not only in fluids but also in solids. So when you read or maybe reading machine design say and try to relate the stress and strain in a metallic bar or a metallic rod, that is also known as that is also termed as constitutive relationship. And if you recall, this relationship is a very similar form to a well-known relationship in solid mechanics. Could anyone please tell me, like, which equation does it resemble the mathematical form? It's a very well-known relationship that you might have read in class 11 and 12 in solid mechanics. Like
Young's modulus?
Yeah, no, it's not Young's modulus. It's actually the Hooke's law.
Sorry, sir, Hooke's law.
Yeah, it's actually the Hooke's.
Constant.
Yes.
Constant.
Yeah, and it's Young's modulus is a constant. So you're absolutely correct. So this is actually the Young's modulus. Yeah. So Young's modulus is also indeed a constitutive relationship in the scope of solid mechanics. And that may also this is not a hard and fast relationship between all the metals. Some metals may not follow the Hooke's law, so they might have to be modeled using different constitutive relationship, and that's why it's very important to know at least know that this Newton's law of viscosity and the Hooke's law are not universal laws for all types of metals or fluids. They may differ from metal to metal, but since most of the fluids, all fluids follow Newton's law of viscosity, and in the case of metals or solid mechanics domain, they follow the Hooke's law in our day-to-day general purposes. That's why we follow these equations and formulate them in our momentum equations, or in this case stress strain equations, to model our problems. So that's the only reason we use this, but these are not universal laws. Okay, that's all I wanted to point out. So I guess anything left? Yeah, kinematic viscosity and Reynolds number. So mu here that I have written is, if you discuss it, it's actually dynamic viscosity. It's actually a dynamic viscosity. So given this, could anyone please tell me what kinematic viscosity is? Kinematic viscosity.
So mu divided by rho.
Yeah, thank you so much, Prasam. It's actually given by mu divided by rho. Yeah, so what does it actually signify? Like, could you please tell what is the significance of kinematic viscosity? Like, we know there is a dynamic viscosity that gives us tells us about the resistance of the fluid to any motion through it, but why we have given so efforts to define another viscosity, or make it more problematic for us by defining another parameter? Why you're defining kinematic viscosity? Could anyone please tell just a vague explanation why, like what does it signify?
Sir, in kinematic viscosity, the mass is not there. I mean, it is not considered. I mean, in that unit, the mass is not there. kg is not there.
Yeah. That's fine. That's also correct. That's also not, I will not say 100% correct, but that's a very like good way approach to explain it in some sense. Yeah, but in a simpler sense, or in a more accurate sense, it actually gives it's an indicator that gives the relative tendency of the fluid to create disturbance in momentum compared to its ability to maintain its momentum. Like, it's just say if there's a body has body with a mass has inertia, right? We apply some force. If the mass is higher, the body will tend to stay at rest. But if our force is higher compared to its mass or its inertia, the body will move. Similarly, the kinematic viscosity gives us a qualitative sense of how, a quantitative sense of the tendency of the fluid to remain at the quantitative sense of the fluid to resist the momentum the momentum that is being applied through the motion of the fluid to propagate through it. I mean, like, if there's a flow through over a flat plate, or flow within a pipe, what will happen is this flow will try to create a disturbance that would propagate and generate a boundary layer, right? Generate a boundary layer, because the presence of the valve will be felt by the fluid by the fluid moving at free stream, and it will tend to slow it down. So this, and as I again mentioned, I guess this diagram will be helpful now. As I told, like, the layer 2, the layer 1 that is being closely attached to the valve will try to slow down the fluid molecules at layer 2. Similarly, the layer 3, the fluid molecules at layer 3 will try to speed up the layer molecules at layer 2. So you can see there is a counteracting phenomena acting on layer 2. Opposing phenomena are acting on layer 2, and there has to be some quantitative understanding to know whether the flow will speed up or slow down given there is a fluid velocity, given the fluid is moving at certain velocity. So to have that general sense, a quantitative sense, we define kinematic viscosity. So is it clear?
Sir,
Yeah.
down. So regarding kinematic viscosity, like for dynamic viscosity, like its speed is higher, then the disturbance will be felt more.
Yeah.
So similar to that, for kinematic viscosity, could you tell like similar relation? If kinematic viscosity is more,
Yeah.
so does it mean that it can't resist the momentum?
No, no. If kinetic viscosity is more, then it will resist the momentum. You see, actually what you told is also right. I'm just giving a understanding. It's actually the same quantity divided by density, just to have a simpler sense. See, if it is kinetic viscosity is given by mu by rho, right? So you have told that if mu is higher, the fluid will resist the motion through it, right? So similarly, if mu is higher, kinetic viscosity will also go high, right? No matter what the density is. For a given density, if mu is higher, the kinetic viscosity will also go up, right?
Okay, sir. So it is similar
Yeah,
relationship.
yeah, it's similar. It's just a way to define in another sense or another way. Yes, it's similar. You will see. Actually, the use of kinematic viscosity would the actual use or will of kinematic viscosity come up when you solve numerical problems or you solve. Say if you become an engineer and now you are trying to, and you are in a say pipeline industry. Say you are in a pipeline industry or, and there may be a standard values of fluid properties given uh, for different kind of fluids, right? Say some fluid there's what some to some pipelines there water flows, to some pipelines there oil flows. So there will be different values, standard values that is given to you, and then you will be asked to model the fluid flow through those pipes. So in those standard notations or standard values, you will see that the kinematic viscosity is like uh, is highly useful to know rather than knowing the viscosity or density separately. Say if you want to calculate Reynolds number, right? Sorry, so I have not mentioned Reynolds number, I guess. So like accordingly, it's good that it came up. It's by itself. So could anyone please explain about Reynolds number? So what is Reynolds number? I don't want the formula. I want its significance. What does it actually tell us? Reynolds number. Yeah. I guess Prasam asks, so Prasam could reply. So what do you mean by Reynolds number?
Sir, it is used for laminar and turbulent flow. Well, to distinguish between laminar and turbulent flow.
Yeah, I get that. For that you need to get certain value, right? I don't want the quantitative part. I want to know its qualitative meaning. I have even pointed out it's a ratio of something. So what is it actually? Ratio of what to what? It should have some quantitative meaning, right? Otherwise there's no point of giving quantitative values to it.
Inertia force to viscous force.
Yeah. Thank you. Thank you to point it out. It's absolutely correct. It's the ratio of inertia force to viscous force. So what do you think the inertia comes from in a fluid flow? Where does the inertia flow comes from?
From the weight of the fluid.
Yeah, you're right in some sense, but in fluid flow, like there's no actual in fluid flow especially there's no actual meaning or significance of the weight of the fluid. It's actually the mass flow rate, not the mass but the mass flow rate. So the mass anyone please, if I have any doubt, please stop me and ask me like what you're writing and we are not understanding it, or what this term actually means. Please stop me and ask. Okay, it's completely fine. Unmute yourself and ask me that. Okay, so mass flow rate. Okay, the actual parameter that is more useful in fluid flows is mass flow rate rather than mass. So it's generally denoted by m dot, and it's given by the density. It's the multiplication of the density of the fluid to its velocity and the cross-sectional area through which the fluid flows. Okay, so you can see the density is the property of the fluid, so we cannot actually play any handle it in any sense. So it will vary from fluid to fluid, so we cannot control it. The cross sectional area is again not in our hand, because given a pipeline or given a requirement, the area of the cross section will fix. Now it will what I'm saying, it will vary from the according to our requirement, but for certain instance or in general sense is usually fixed. The only parameter that is in our control is the velocity. Okay, and it is the velocity, in this sense at least, that's what creates the inertia force. We say, right, you will get to know as you like proceed further in the course that for a flow through flat plate, it is the inertia of the flow, it is the mass flow rate of the flow that drives the flow. For a flow through pipe, it is the pressure gradient that drives the flow. So any parameter of flow that drives the flow generates the inertia force. Okay, the driving factor of the flow. And in some sense you are absolutely right, it's related to mass, but it's not actually the mass. Okay, then viscous force. So which parameter determines or signifies the viscous force in a fluid flow? I guess the name itself, yes, the name itself suggests, viscosity. So as the viscosity of fluid increases, the viscous force or the resistance of the fluid for a motion through it increases. Okay, like if the viscosity is higher in this, say in this pipe flow, if the viscosity is higher with the resistance to this fluid flow. Okay, I'm just pointing it out as U. Say the U is the velocity of fluid. So higher the viscosity, higher the resistance the fluid faces to pass through this pipe. Okay, so Reynolds number is basically the ratio, or it gives us an idea which among the two dominates the flow. Okay, so if the inertial force is higher, as you have naturally pointed out as laminar turbulent flow, as the inertial force is higher and the viscous force is lower, the fluid will inherently try to be turbulent. But for now this definition is correct, but as you go deep in fluid mechanics, you will get to know like there are various parameters or various actuating mechanisms that creates turbulence, and it's not only the inertia force itself that creates turbulence. Okay, but for now it is fine for you to know as the inertia force increases, the turbulent nature of the flow increases. That would be a correct explanation. So yeah, that's fine. So see, and in a mathematical form, Reynolds number could be defined as rho v L LC, actually LC by mu. Okay, where rho is the density, v is the velocity of the flow, LC is the characteristic length, and mu is the viscosity, dynamic viscosity. You can write this again as, am I correct? Right, you just bring this down and you can write it as mu by rho, and this will be then could be easily written as where nu is the kinematic viscosity. So I guess now you understand the significance of defining kinematic viscosity rather than viscosity alone, right? So if you know the kinematic viscosity, and it is a standard parameter that is being given in all standard charts for fluid flows, the kinematic viscosity is a standard parameter that has to be given. So rather than finding out the viscosity and the density separately, because again density is also sensitive to temperature, so you just cannot have a say you are finding you have to find the viscosity of fluid at 100 degrees Celsius, but you know the density of fluid at only at room temperature. So again, you have to find or extrapolate the values of the density to 100 degrees Celsius, then find out the kinetic viscosity, or to then find out the Reynolds number. So to make our life easier, the researchers or scientists have found another parameter that is new, which is a ratio of the dynamic viscosity to its density, and it's a standard parameter that is being given in the chart. So rather than finding out dynamic viscosity and density separately, you just need to know the kinematic viscosity. So once you know it, it's very simpler. Life becomes very simpler. You need only 3 parameters to calculate the Reynolds number. So is it clear, Prasam, that why you define kinematic viscosity, and how is it similar but yet more helpful than dynamic viscosity alone?
Yes, sir. Thank you, sir.
Yeah. Thank you so much. It's fine. Okay. So I guess all the concepts regarding week 2 has been discussed. So now we will straightly go to some examples, and please help me out to solve them, and we can make the class as interactive as it was, as it has been till now. So please help me out, everybody. So yeah, I guess, yeah. So is the screen visible? The question, is it visible? Is the
Yes. Yes, sir.
Yeah. Okay. So you can also go through the questions, but I will just dictate it in a sense that it is more clear to everyone. So I will just dictate it, and you can also go through the question. Okay, so that's completely fine. The viscosity of the fluid is to be measured by a viscometer constructed by 240 centimeter long concentric cylinders. Okay, I'll just underline it. So some key terms. Concentric cylinders as given below. The outer diameter of the inner cylinder is 12 centimeter, and the gap between the two cylinders is 0.15 centimeter. Okay. The inner cylinder is rotated at 300 rpm, and the torque is measured to be 1.8 Newton meter. Determine the viscosity of the fluid. So the diagram is given here. L is basically the gap that has been given as 0.15 centimeter, and yes, and we are asked to use the following assumptions. Consider a fluid layer of thickness L, that is already pointed out, within a small gap between two concentric cylinders. Take the wetted surface of the inner cylinder to be A equal to 2 pi RL. So it's basically a lateral surface area of the cylinder, by disregarding the shear stress acting on the two ends of the inner cylinder. Yeah, where L is the inner cylinder. Okay, so I guess you have read the questions. So you can, if you know the answer, you can just work it out. It's completely fine. You can tell me the answer, but I will just again try to simplify the question, explain the questions a bit clearly to everyone. See, what it basically means is there are two concentric cylinders. So concentric basically means there is a cylinder within a given cylinder. Okay, that what basically means by concentric cylinders. Okay, or concentric basically means there actually the centers of both the geometries coincide and both of them have different radii. Okay, it can be sphere also. There can be concentric spheres also. So this is a concentric cylinder. So in a 3D view, or it could be told as like this. Yeah. So this is basically what is meant by concentric cylinders. So these are two cylinders, and these two cylinders are rotating. Okay, inner cylinder is rotating. Okay, in this case, inner cylinder is rotating. Yeah, that's fine. If I use different color, so it is helpful. Yeah. The inner cylinder is rotating. Okay, So it has a length of 40 centimeter long. Yeah. And we are asked to disregard the shear stress acting on the two ends of the inner cylinder. Then we can disregard the stress that are acting in the ends of the two cylinder. Okay, you can just disregard it so that the problem becomes more simpler. And because again the the ends might be not cannot be modeled as simple as the rest of the portions, then that's why again dimension of the, that is the length, is much larger than the gap between the two cylinders, so that we can just assume we can ignore the effects, the end effects of the two cylinders. That basically means if the cylinder is much longer, the length of the cylinder L is much greater than the gap between the two cylinders, we can easily just ignore the effects of the ends and assume that the flow around the ends of the cylinder won't affect the flow within the cylinder. Okay, within the gap within the cylinders. So is that clear? Why we can take this assumption? Like, see, if the cylinder was too small, if the length of the cylinder was too small, say just like this, so you can see this, if this is L and this is, say, the gap is given by G, then L is like not that greater than G. Okay, it's comparable size, and because of which, say, the rotation of the inner cylinder creates a fluid flow, say rotational fluid flow, and maybe some, okay, I'll just zoom it out. Yeah, it will be better. The rotation of the inner cylinder would obviously create a rotational fluid flow around it, throughout the cylinder actually. Throughout the cylinder it will create rotational fluid flow, but again, since it is at the end, it might happen that they may again create some vortices or rotations perpendicular to the original rotation that has been created because of the rotation of the cylinder. So there may be some perpendicular eddies or vortices because it is at the ends. The ends might create such fluid flows, and because of such vortices, this may create a further complicacy while evaluating the fluid flow in the region within the cylinders. So again, because of these ends are too close to the region where we want to solve our problem, this may create this may act as a bottleneck that would make it difficult for the problem to be solved. Okay, so to make our life simpler, we have been told that we can just ignore the effects of the flow that is being generated at the ends of the cylinders. So that we can just nullify or omit the effect that has been created because of the ends of the cylinder, and that could happen only when the length of the cylinder is much larger than the gap between the two cylinders. Okay, so I guess it is clear, like when we can take these assumptions. It is not given always be taken for granted that we can always ignore the end effects. No, even if you are given a problem in the exam and you're telling that we're ignoring the end effects, then you should mention why you're ignoring the end effects. Why so? Why not include the end effects? You can mention that we take the length of the cylinders to be much larger than the gap between the cylinders, and that's why we can comfortably assume that the fluid flow within this region is not affected by its ends. What's happening at its ends. So we can then given this assumption, we can solve the fluid flow problem in this region. So I guess it's clear. So yeah, I'll just take a, yeah, try to solve it here. I guess it will be better. So let's try to draw the diagram again. Have anybody solved it?
Sir, option D.
Option D. Let me see. What is the option?
0.158.
Okay. Thank you, Prasham. I guess it is right. I also don't know, but let's see. Let's, for the sake of let all others to also know, we'll try to solve it. Okay. But very good. Like if it is correct, I guess it is correct. So yeah, we'll just try to solve this one and just then take on other problems for others to solve. Okay. Yeah. So who have not solved it or do not know how to approach, we just look at this illustration. Okay, so that's fine. So here given given that the length of the cylinders are taken to be 40 centimeter, the outer diameter is it diameter? Oh, inner, sorry. The outer diameter is not given, so that's fine. The diameter of the inner cylinder is given to be 12 centimeter. The RPM, or the rate at which this inner cylinder rotates, is given to be equal to 300 RPM. RPM is basically rounds per minute. And the torque, yeah, is anybody speaking? The torque is measured to be 1.8 Newton meter. Dhanlakshmi, are you speaking? Is there any doubt? Dhanlakshmi?
Problem outer diameter of 12 centimeters noted, sir.
It's outer.
Yes, sir. Outer diameter.
Yeah, it's outer diameter of the inner cylinder, F right?
Of the inner cylinder. Okay, sir. Okay.
Thank you for pointing it out, but I also show it now only. Yeah.
Outer of the inner cylinder. Okay, sir. I understand.
Okay. So the torque measured is 1.8 Newton meter. Yeah. So the torque is a very trivial formula. The torque is given by the force applied to the perpendicular distance of from the point at which the force is applied. So it is basically the radius of the cylinder. Say if it is the center, then the perpendicular distance at which the force is being applied would be, I'm sorry, it is wrong. Yeah, the perpendicular distance at which the force is being applied is basically the radius of the inner cylinder, so that's fine. Yeah, and then again, this force that would be that is required to rotate this cylinder would be given by what? Like as Prasam has solved it, so what would this force be equal to, Prasam?
Shear stress into area.
Yeah, absolutely correct. Yes, shear stress into the area. And how you have calculated shear stress, could you please tell us? Like, tell me, I also don't know, please.
Sir, Newton's law of viscosity, mu du, right?
Okay, you're telling this is tau would be equal to mu du by dy, right? So
Yes.
what is du by dy?
Velocity gradient, velocity by the gap.
Oh, yeah, but why you have assumed the velocity to be say why you have assumed the velocity to be linear?
It is given a small gap.
Yeah, thank you. Yes, yeah, you have rightly pointed out. Yes, for a small gap, we can assume the velocity profile to vary as I guess you have taken the velocity profile to be equal to, say, v is the velocity, then y by gap is, I guess, it is denoted by L. Yeah, so I guess this is what you have taken the velocity profile to be, right, Prasam?
Yes, sir.
Yeah. Yes. See, it's absolutely correct to take this assumption because the gap is much smaller than the length of the pipe. Okay, but in general sense, it is not the case. Okay, sometimes the velocity profile may have a different profile rather than linear. Okay, it may be parabolic, it may be exponential. So for that you need to find out, or if it is not given, if it is not linear, it will be explicitly given. Okay, or sometimes for you need to solve the Navier-Stokes equation, as you will, I don't think you will solve this in this course, but I don't know. If you have taken a fluid mechanics, you will know that you need to solve Navier-Stokes equation to find out the velocity profile. But since this gap is much smaller than the length of the pipe, we can assume the velocity profile to be linear, and you will know this velocity profile resembles a simple coed flow. If I am not wrong, this resembles the velocity profile of a simple coed flow. And funnily enough, this type of flow, where the flow is generated by the rotation of the cylinders, where the flow between the two concentric cylinders has been generated by the rotation of one of the cylinders, are known as Taylor-Coed flows. Okay, this is a very standard type of flows, like they are plain Poiseuille flows. Sorry. They are Hagen-Poiseuille flows. Then flow or flat plate. And there are many others, like, but for the scope of this course, this basic fluid mechanics course, these are the standard ones that you will solve. And Taylor-Coed flow is also one of the standard fluid flows whose velocity profile will usually know, but it's not actually this. But since we have, and obviously Coed flow, yeah. But since it is given that the gap between the two cylinders is much smaller than the length of the pipes, we can assume the velocity profile to be linear. Okay, and in most of the cases, if the gap between the, say, two flat plates, or gap between the two cylinders, or any geometries are too small, you can correctly approximate the velocity profile to be linear. Okay, this is a very helpful guess while solving fluid flow problems where the velocity profile is not given, but the dimensions of the fluid flow problem are given. Okay, so yeah, so given this, the given u is equal to Vy by L, you can just take the derivative of it, and you will find that this will be equal to mu du by dy will be equal to mu V by L. And if you, and again, since V is not directly given, you need to find out V. So here V will be the angular velocity of the inner cylinder because of its rotation, so would be equal to mu omega r by L. where omega is the angular velocity. Okay. I guess now then everything is very easy. Just we need just need to substitute the values. Then torque is given by shear stress into area into the radius. What I have taken as small r. Okay, I will take it as capital R. Maintain the uniformity, right? Yeah, capital R. Yeah. Then tau is given by mu omega r by L. Then A, they have asked us to take the lateral surface area of the cylinder. So it will be 2 pi RL. Then there's again one more R. So it will be basically be equal to mu omega. Then there are 3 R's. Then it will be R cube 2 pi L, if I'm not wrong. And O, sorry, this is not capital L, this is small l, the gap distance, right? Small l. And we are asked to find a viscosity. So mu would be equal to the torque divided by this will be multiplied by L, then divided by omega r cube by 2 pi L. Yeah. So what is torque? Torque is 1.8 Newton meter. L is 0.15 cm, right? 0.15 into 10 to the power minus 2, since it is centimeter. Omega is 2 pi, n is 300, since it is rpm, divided by 60. R cube, radius is 12 I guess 6 centimeter. 6 into 10 to the power minus 2 whole cube into 2 pi into 40 into 10 to the power minus 2. I guess it's right. And what was the answer? It is 0.158, right?
Yes.
Yeah, 0.158. It would be kg meter second. I guess the units are also right. So I guess this is it. Or I guess again, or you can write Newton second per meter square. It's also fine. These are both are correct only. So yeah. So I guess it is clear now. So let's go on to the next question. So yeah, just mark out the questions. This question number 1. This is 2. And this will be 3. Yeah. Yeah. Consider two identical small glass balls. Okay, glass balls. Again, these are important terms. Okay, in the question. Identical small glass balls, glass also, dropped into two identical containers. One filled with water and other filled with mustard oil. Which ball will reach the bottom of the container first? It's very qualitative question, and trying to understand the conceptual clarity of the students. So it's very easy actually, but whichever options you choose, I need explanation from you. So please see the options and tell me the answer. It's very easy but very conceptual also. See, there are key terms. Identical small glass balls dropped into two identical containers with water. One container contains water and other contains mustard oil. So identical containers basically means the height of the containers and the dimension, everything is identical. Dimension of the containers are same. Get it? The dimensions of the container are the same. And you have dropped two glass balls in the container. One contains water, the other contains mustard oil. I guess all of you have seen water and mustard oil. So, and you know the nature, how they behave, how they flow. So please, it's a very trivial question but very conceptual also. Please tell me, what would be the answer? Dhanlakshmi, Prasham, Rohit.
One with
What?
sir, option a B.
B.
Water will reach first.
Oh, why you say so?
Because in oil the viscosity is more, so it will resist the motion.
Yeah, absolutely correct. Yes, you're right. The since again, see, this question is very simple and actual your answer is absolutely correct. But you need to look what are the assumptions that the question has taken for us to come into this conclusion. See, there are two identical small glass balls, identical small glass balls. It basically means the dimension of the glass balls are small plus their mass is same. Okay, it's not like that the one is circular, other is cuboidal. Then also the mass could be same, but the shape varies, and when the shape varies, the resistance, yes, the drag force that acts in the body will vary. Okay, so it's also important. Identical are dropped into two identical containers. Again, it might happen that one container is very, what to say, has a very small radius, the other has a very large radius, and also they might differ in height. Then also dynamics of the problem changes, right? There's no comparison in these two cases. Even though it has the mustard is too has high viscosity, it might happen that the glass the glass tube the container containing the glass might have a very large depth compared to the length of the container containing the mustard oil. So these things you need to keep into focus, keep into consideration. Okay, and yeah, since the viscosity is higher, so the ball the ball dropped in a mustard oil will have lower velocity. But if you remember, like, I guess everybody is every one of you is in the second year of your degree, or might at least have taken a have done an experiment. If you anyone of you done an experiment known as the finding the viscosity of fluid. Have anyone of you this anyone of you have done this experiment in your physics lab or mechanical lab, finding the viscosity of fluid using this same phenomenon? You dropped three different balls, one may be metallic, one may be glass, one may be of any other different, say, plastic, and find out the time it takes to reach the bottom of the container. Have any one of you did this experiment? That's fine. Now I'm just saying because it's very popular experiment that people use to find the viscosity of a given fluid. Okay, so I will just give you a basic overview just to let you know why the term small is important. Okay, they could have given two bricks dropped in two large containers containing one containing mustard oil, one containing water. Why they have specifically mentioned it to be small? Okay, so this contains water and a small glass ball is dropped. Okay, small glass ball is dropped. So once the ball is within the water or within the liquid, what are the forces that acts on this glass ball? See, if I draw a free body diagram of the glass ball, what are the forces that might act on this glass ball?
The gravitational force, weight.
Okay, then
The viscous force.
in which direction will it act? This direction or this direction? 1 or 2?
So 1, sir.
Yeah. Is there anything else?
If the ball is accelerating, then
Yeah. The ball is not accelerating. The point at which I want to find I want to balance these forces is a point at which the ball is not accelerating. So what is the other force that might act? The ball is falling in a liquid. What kind of force a body experiences when it is in a
buoyancy
liquid?
force.
Yeah, thank you. The buoyant force. Okay. FB, then viscous force FV. So equating, and I am finding I'm equating this forces at the point where the acceleration is equal to 0. Okay, the ball is falling with a constant velocity. So at this point, if I equate the forces, FV plus FB would be equal to mg, right? And I have taken the ball to be spherical. So the viscous, again you need to know this. The term small, right? The body or the ball is taken to be small. And for such small bodies, the viscous force has a very famous, the viscous force can be found by using a very famous expression given by G.G. Stokes. If you know, it's very popular because the very fundamental cornerstone of fluid mechanics is given by the Navier-Stokes equation, and G.G. Stokes is one of the other scientists, one of the scientists upon whose name this equation has been named. So G.G. Stokes have given an expression for finding viscous force in a spherical body, in a small spherical body flowing through a viscous fluid. Okay, so it is given by 6 pi mu r v. Okay, so given this f is equal to 6 pi mu r v, see, I'm saying for a small dimension. If the body is big, then we have to find an expression for the viscous force by using a Navier-Stokes equation. But for a small body flowing with a constant velocity and at a viscous fluid is given by this expression. Okay. So given this, then we can just equate all the forces. Then this 6 pi mu rv plus buoyant force will be equal to the rho v, the volume of the fluid that is displaced by the body, into g by the mass would be, the gravitational force will be equal to, okay, it would be actually volume of the fluid, then volume of the fluid, and then g, then it will be equal to density of the body, volume of the body, and the gravitational force. So given that the ball is completely submerged in the liquid, then Vf would be equal to Vb. The volume of fluid displaced will be equal to the volume of the body itself. So you can just then write it as 6 pi mu rv would be equal to volume of the body would be given, since it's spherical, so 4 by 3 pi r cube, density of the body minus density of the fluid into the gravitational force. If I'm wrong, just point me out. Okay, then the viscosity of the, no, we are talking about velocity, right? So the velocity then is equal to 4 by 3 pi r cube rho v minus rho f g divided by 6 pi mu r. Then r would cancel out, this would become square, pi would go out, then this will become, sorry, I can just cancel this also, it's fine. It will become 2, it will become 3, then it's basically 2 by 9 r square rho b minus rho f g divided by mu, and this is the velocity. So more popularly, this velocity is also has one name. This called as the terminal velocity. Okay, terminal velocity. It is actually the highest velocity, the highest constant velocity by which with which a body falls through a fluid. Okay, this is terminal velocity. So see, as Prasham has pointed out, and I guess everyone also have pointed the same answer, that the body, the glass ball in the mustard oil will reach slower, will reach later than the glass ball at the dropped in the water. It's because simple. See, all the other parameters are same. Balls are identical. Density, density also plays a role. There's also one thing. And say this term is not that significant. Say in fact the density density of the oil is around 800 kg per meter cube, and water is around 1000 kg per meter cube. Sorry, density, okay, not viscosity. And the density of the body remains the same, so this actually does not play that much role, and gravitational force remains the same. The only factor that directly or has a significant effect is the viscosity. So as the viscosity goes up, the velocity will go down, and as velocity goes down, it will take larger time for the body to reach the bottom of the container, or in simpler terms, it will take a larger time the body to reach a constant velocity or terminal velocity, and then reach the bottom of the container. So is it clear? It's a very simple experiment that we do, but is it clear? This is a mathematical expression of what you intuitively answered. Okay, I guess it's clear. So let's go to the third question. Yeah, it's a very interesting question. Yeah, a thin 20 centimeter by 20 centimeter flat plate is being pulled at 1 meter per second horizontally through a 3.6 millimeter thick oil layer sandwiched between two plates. One is stationary and the other is moving with a constant velocity of 0.3 meter per second. The dynamic viscosity of oil is 0.027 Pascal second, and the location where the oil velocity is 0 is, yeah. So given in this diagram, intuitively, where do you see the velocity of the oil is equal to 0? At what point? It is also pointed out, but just wanted to know that, seeing the diagram itself, can you please point out where the velocity of the oil is 0? Anyone? Just look at this diagram or the velocity profiles. Could you say where the velocity of the oil is 0? Then Lakshmi, Prasham, Rohit, anyone? Yes? Say I pointed 1, 2.
Sir, at point A.
Okay. Thank you, Dhanlakshmi. You are correct. You can read yourself. Yeah. So, like, if you are considering the whole geometry, then there are actually 2 points where the velocity of the oil is 0. At point A, as well as at this point, at the wall. It's a bit, I asked in a tricky way, but at here is also, okay. At here also the velocity is 0. But they have mentioned location where the oil velocity is 0. Okay, so they explicitly want to know this point within the, say if we change the control volume as this one, so within this control volume where the fluid velocity is 0. So you're right, at point A it is 0. So you need to find out point A, the location, basically the distance of point A from the lower wall, given these conditions. So could you please find out what is YA, this dimension?
So A.
0.6 mm from bottom one. Okay, let me check. I also don't know. So how did you find out?
Sir, similar triangle.
Okay, say similar triangle. Yeah, it's good only. Say if I game it as 1, 2, 3, 4, 5. Okay, B, C, D, E, F. So which among the two are these three triangles? You say are the similar triangles.
So bottom two, sir. ABC and AD.
Okay, ABC and ADE. Okay. So Prasam, since you found out the answer, could you please help me out step by step how you approached it? So everyone should know, and I can also learn. Yeah, tell me how you use the concept of similar triangles here and found out why it is the y equal to 0.6 mm from the bottom wall. Yeah.
So taking the two sides, the velocity, one divided by the distance A to 0.3 divided by distance AC.
Point A to C. AC. Okay, AC by, I guess it will be AE then, is equal to what are other two? Okay.
0.3 by 1.
Okay. BC by ED. Yeah. Then AC and AE. Then AC would be equal to YA. AE would be equal to, I guess, 2.6 minus YA. Then BC is, okay, tell me what BC would be 0.3 or minus 0.3.
0.3, sir.
0.3. Okay, you're just measuring the lengths. Okay, that's fine. Yeah, and it will be BC is 0.3 and ED would be equal to 1. Okay, so it's very simple. So if we solve it, I guess YA would be equal to 0.3 into 2.6, I guess 0.78 minus 0.3 YA. That will be equal
Hello,
to,
sir.
yeah, Ranjan. Oh, who is it? Rohit. Yeah. Yeah, Rohit. Please tell what happened. Okay, I guess it's fine. Okay, then thank you, Prasam, Rohit, everyone who helped out. That's fine. So let's see question 4. In the previous question, the force that needs to be applied on the plate to maintain its motion is, yeah, see the options and just help me out. This is a geometry. You need to find the force that is required to pull this plate within this fluid layer. Okay, let me try to solve myself also. Let me draw the diagram. It'll be good. So I guess I have to speed up a bit also. Time is running out. So. Question number 4, right? is a plate. Everyone please also try to solve it. You can just take the take the screenshot of the question, screenshot, or just click a photo from your mobile phone or any device and just try to solve it. Or else I'll just stop. I'll just wait for a while and wait answer from one of you and then see.
So,
if it,
could
yeah,
you please scroll up, sir, a bit?
up. Okay. Is that fine?
Yes, sir.
Okay.
Sir, is it 1.62 Newton?
Okay. What Newton? C. Let me check.
Yes, sir.
Yeah. It is 1.62. So everyone else also got 1.62. See, if you don't respond, then I will assume that you have got the answer. So I will just skip it. Like if you have any problem in any step, you can just point it out. Then either me or like since Prasham also solved, she can also help you out. So that should be the ideal way by which we take the session up. Like if you don't respond, then I will assume you have done it. So I will just skip the question and go to the next question, I guess. I should do like that only, I guess. But I will just give you a vague idea because I should not spoon feed you every steps. Okay. So the thing is, since the plate is moving, the plate is being pulled by a force F, it will experience a resistive force, right? Because of the viscosity of the fluid. And the viscosity, again, we know is the viscous force, I should say, in this case, or the shear force that will be given by shear stress into area. And shear stress, we assume that the fluid is Newtonian. Since the in question is not strictly given, but you can, if not given, you can assume it to be Newtonian and just mention it. Okay, we assume the fluid is Newtonian, and then we apply the Newton's law of viscosity to find out the shear stress, and the area is explicitly given here. It is equal to 0.2 meter into 0.2 meter. It's fine. 20 centimeters is same only. So yeah. So you need to find out the shear forces. Again, see, since the plate is moving through the layer, there are two phases at which the plate experiences the shear stress or the shear force. Okay, that would be in this region and in this region itself, both the upper and the lower surface. Okay, so you need to find out F shear upper or 1 as per your convenience, you can name it, then F shear lower. Okay, and once you find it, you just need to add it up, then just it will equal F shear total would be equal to F shear upper plus F shear lower. Then Prasham, since you have solved it, can you please tell me what how the velocity profile is how you have taken the velocity profile to be?
So for upper, it is 1 meter per second by 1 mm.
Yeah, so I guess you have basically taken it to be v
Ye-
y by h1, right?
Yes, sir. Yes, sir.
And for lower surface,
For lower surface, it is 1 by AE.
1 by
E.
AE.
AE.
AE. Okay, 1 by AE. Hmm. 1 by AE should not be the case, right, Prasam? Why you have ignored this part?
Sir, to get the slope, sir. The profile is not uh, the different slope, no, sir, for AED and ABC.
Wait, huh? Yes. What you are saying? AEN?
Slopes are different, no, sir, for above and top triangle.
No. I know. But while for measuring the shear stress at this region, for the lower surface of the plate, why you have ignored the velocity profile at this region also? You have just taken it 1 by AE. Why not include this part also? No.
In the lecture, it was mentioned that if while taking the slope, we should take the one which is like at the plate. At the plate.
Okay. I guess it's fine if you're getting the answer is fine. But actually, the thing is, see, you have taken the velocity profile to be linear. Okay, you assume the velocity profile to be linear. Then it is basically equal to v lower, I should say, y by h. Then you need to see, in this case the velocity varies from 0 meter per second to 1 meter per second. But in this case, the plate is moving with a velocity equal to minus 0.3 meter per second, since it is moving in this direction. And here the plate is moving with a velocity of 1 meter per second, right?
Yes, sir.
Yes. So since it varies linearly, then this should turn out, this will come up as okay, sorry. Yeah. So, and while if we take a derivative, the y will get cancelled out, so it will just be for lower part, okay, tau shear lower would be equal to mu VL by H. And for finding this VL, I guess you need to take into consideration the net change that has been taken, that the velocity profile has gone through from the lower plate to the upper plate that is being pulled. Okay, so that would be equal to mu, I'll just write it, it's very congested actually, it will be equal to mu 1 minus 0.3 by, it is 2.6. So if you do it by this, does it come out to be different?
Same, sir.
Same. Then how could it be same if you're not including the effect of 0.3 meter per second? Okay, that's fine. I guess you may just check it, or I will also check it again and just clarify in the next class. But you need to take like this, okay?
Okay, sir.
Okay. Thank you. It's correct only. So yeah. Okay. Again, it's very simple question. This only dimension analysis. I guess everybody are here done. So please tell me as fast as you can. Question number, it is 5. 5, I guess. Yeah. Question number 5 is very simple. Please. What is the dimensions of kinematic and dynamic viscosity?
B.
D.
B, sir. B. Second one.
B. Yeah. Yes, absolutely correct. So it is correct. So kinematic viscosity is unit is meter square per second. So by okay, I'll write it like this only. So its dimension would be,
Yes, sir, right.
yeah, thank you. It is correct. I'm just writing it, okay? Please don't mind. It would be L square by time, that is L square T inverse, right? And for dynamic viscosity again, what it is? It is shear stress by the velocity gradient, right? So it will turn out to be shear stress is basically the same unit dimension set as pressure, so it will come out like this. And dimension is same as pressure, okay? They both are not same. Both do not have the same physical meaning, okay? I'm just saying like that. Dimensions are same because basically units are same. And then velocity gradient will be as velocity is meter per second by meter, then you cancel out. This will cancel out, v1 it will be equal to ml minus 1 t minus 1. I guess it is correct. Yeah, thank you Prasam and whoever else. I saw it, couldn't see your name, that's fine, thank you. Okay, question number 6. Oh, it's again very simple. It's match the following. Yeah, seeing these different types of fluids, just tell me the right option. Match the following. Take your time and give me the correct option.
C, sir. C.
C.
See, sir.
Okay. Good then. Thank you. Okay. Just I will write again. P is 2. Okay. Then P you are saying it is Newtonian. Q is 4. Q is Europlastic. Oh, I guess you have taken the lectures very seriously. You are very fast now replying. Thank you everyone. R is 5. R is plastic fluid. Then S is 3. Dilatant fluid. Okay. Okay, any examples for each of them? Dilatant fluid, any example?
So starch solution, is it dilatant?
Starch. I actually don't know, but if it is, then very good. Starch, just right. I don't know. Okay, I also don't
Sir,
know.
plastic fluid, sir.
Yeah, example. What is it? Do you know? Tell me. Plastic fluid. What is the example?
Yes, sir.
Toothpaste, sir.
Oh, no. Toothpaste. I guess it was Bingham plastic. If you remember clearly, it is saying plastic or ideal plastic.
Yes, sir. Plastic.
Yeah. What is the example for plastic fluid?
Oh,
Say.
cylinder, sir. Cylinder.
Cylinder. I guess who is speaking? Ranjan. Sorry, Ranjan. Cylinder is not a fluid. I don't know what you're talking. I don't know. So
It's okay. Okay, sir. Okay.
okay, we'll look through it again. You join the next week. Okay, we'll find out a good example for plastic fluid. Okay. So it's fine. It's fine. Who is speaking? Done. Okay. So question number 6.
भाई कोई वीक 3 का आंसर दे सकता है?
Hers, we cannot give the answer of week 3 solution. So if you have any particular doubt, I guess I have given a email ID. You can mail me there. Give the screenshot. I'll give you a conceptual means understanding of the problem, and then you can work it out yourself. Okay, like here we do not.
Sir, solution. This is assignment 3.
Who is it speaking? Ranjan. I told you, Ranjan, I
Yes, sir.
cannot.
Solutions.
Huh.
Yes, sir. Sir, solution this assignment 3. Just a problem.
Yeah, that I cannot give, no.
It is mentioned in the forum that for upcoming assignment solutions shouldn't be given.
Yes, Ranjan.
Yes, 3, sir.
Yes, I cannot give you the answer, right? If you have any doubt, just ask me in the mail ID. I have mentioned you, right? Just send me the question. I will
Okay, sir.
reply you. Don't point it out
Okay, sir.
again and again.
Okay, sir.
Okay? Don't mind, please.
Okay, sir. Okay, sir.
Okay, then question number 6. There are assertion and reason type questions. It is first question tells that the blood is a Newtonian fluid. Second tells the rate of strain varies non-linearly with shear stress for blood. So it's again a very simple question. Please tell me what is the right answer and give your reason. Last one. A is false, R is rare. Thank you. I explicitly pointed out that blood is not a Newtonian fluid, so this is wrong. But again, the rate of shear strain varies non-linearly with shear stress for blood. Yeah, tau is equal to mu theta to the power n. I don't know exactly. Does it follow exponential relation? Yes.
B, sir. B. Both of it
No.
are intelligent arts, not the correctly included.
No. B is not right. Okay. D is true. Okay, Ranjan. Blood is not a Newtonian fluid. B is not correct. Okay.
Okay, sir.
Blood is not Newtonian. So yeah. So blood is not Newtonian, but the rate of shear strain does not vary linearly. It varies non-linearly with shear stress for blood. Keep this into mind. Okay, it's very trivial question, but it comes out frequently in entrance exams or interviews. It's very important for you to know. Okay, you are to exam. Okay, statement 1. At the standard temperature, kinematic viscosity of air is greater than that of water at same temperature. This is one statement. The dynamic viscosity of air at standard temperature is lower than that of water at the same temperature. This is the second statement. So again, please choose one of the options, which one is correct. And
So 1 is false, 2 is true.
1 is false, 2 is true. Let me see. So kinematic viscosity is greater than at certain temperature. The kinematic viscosity of air is greater than that of water at same temperature. I guess it is not the case. I guess both are true. Okay, let me check. How did you say it, Prasham? Can you please tell us why you say so?
No, sir, just I thought maybe water has more viscosity compared to air.
It is kinematic viscosity, right? You know, kinematic viscosity. It is divided by density, right?
Oh, okay, sir.
You need to take into consideration density also, right?
Okay. Right. I thought of only viscosity. I didn't.
Yeah. Think about it and say now what is correct. C is not true. Okay, I guess actually for this you need to know some relations or ratios or particular values for how the density of air is related to density of water and how the density of water viscosity of water is related to viscosity of air. Okay, so in general sense, in order of magnitude sense, the viscosity of, as you're right, viscosity of water is greater than viscosity of air. So viscosity of water is around the order of 50 times viscosity of air. Okay, also if you solve some fluid flow problems, you may know that the density of water is around is actually 1000 kg per meter cube, and air is around 1.2 kg per meter cube. And for our understanding, let's take it to be 1 kg per meter cube for simpler calculation, right? So mu air by mu water is 1 by 50. No, I'll write it correctly, otherwise people might get confused. Mu air by mu water. So what was first assumption? At standard temperature, dynamic viscosity of air at standard temperature is lower than that of water. So this is correct. This is correct, right? This is correct. Just to check the first statement, then it is rho water by rho air. So it is 1 by 50 into 1000. Sorry. Then it comes out to be 20. So I guess 1 is also correct then, right? At standard temperature, the kind of viscosity of air is greater than that of water at same temperature. Okay, temperature is very important. Same temperature. Okay, then I guess this is A is correct. So okay, keep this into mind. Okay, for next time when you just see such problems. Okay, I guess this was 6. Okay, I guess this is all for today, I guess. So thank you again everyone who has joined to today's class.
Thank you, sir.
Thank you, Ranjan. And
Thank you, sir.
just mail me, okay, your doubt. I will clarify you, okay? Just doubt, not the solution, but your doubt, okay?
Okay, sir.
Thank you for joining.
Okay, sir.
And Prasham,
Yes, sir.
last week also you joined, and I guess you Harsh, I guess I gave the email ID in the chat. You just can scroll up. Yes, it is this Abhishek Sarkar 4@gmail.com.
Person, please send me mail ID.
Hello.
Just to speak, person. Email ID send me, please.
Sorry, but if there is any doubt, you can ask it in the forum also, right? There's discussion forum.
Just okay. Any doubts or assignments?
Yeah, you can ask it in the discussion forum also, right? That time it could be of help to everyone, and we can reply also.
Okay.
Okay. What is?
Email ID of news. How to contact some numbers?
I'll give an email ID. Contact number I cannot give. So just mail me, okay? I won't mind. Just mail me. And Ranjan, as Prasham rightly pointed, you can just take your doubts to discussion forum
Okay,
also,
sir.
or
Okay,
just
sir.
mail me. And Prasham, hello.
Okay, sir. Okay, sir.
Yes, sir.
You last time, if I remember clearly, you pointed out regarding for a stationary fluid, del dot v would be 0, right? Last session. So if you might have forgotten, it's just fine, but I just need to tell you that you are right. Since the fluid is stationary, I don't know, someone would have pointed out, but I just want to clarify the last week's doubt. It was, since the fluid is stationary, all the components of velocity are 0, right? So del dot v inherently becomes 0, whether the fluid is compressible or not. We don't need to consider the compressibility, but because the fluid is stationary, the del dot v product inherently becomes 0. So then you can just, the only stress that acts on the stationary fluid becomes the pressure. If you recall, I just wanted to clear, okay? I guess that's fine.
Yes, sir. It was regarding some something project, but I forgot, sir. If there is doubt, I will ask it in next class. I can ask it in next class also, sir.
Yeah, sure. If you have any doubt regarding today's class, and if you join my session next week also, you can just carry forward your doubt and tell me, okay? Just as I give a room for 5 minutes at the start of a class for doubt clearing. So you can just join there and just ask the doubts. I will clarify.
Okay, sir.
Okay, Ranjan, thank you.
Okay, sir. Thank you,
sir.
Tarun, thank you, and Prashant, thank you. Okay.
Thank you, sir.
Meet you next week. Okay.
Thank you, sir.
Okay.
Thank you, sir.
Okay.